right, BWSI. Welcome, welcome, welcome. So, I want everybody to settle down here. And what is BWSI? Transformational. Yes, I'm glad. Thank you for doing that for Dr. Mary Knapp. It's great that she's here today. It's great that everybody else here is today, too. I've known Mary for a few years now. We've been keep crossing paths in various outreach events, both here at BWSI and on MIT's campus. Mary works at MIT Haystack Observatory in Westford, Massachusetts. Does anyone know where Westford is? We might even have a couple of students from Westford. Yeah, we got it, okay. There's actually a lot of science that goes on out there. I've worked at the Fire Pond facility for a while, myself at Lincoln Lab. There's the Millstone Hill Radar Complex where they're tracking deep space objects. And hopefully Mary will tell a little bit about Haystack as well and the project that she's got going on. So super, let's have a round of applause and welcome for Dr. Knapp.
All right, hi everyone. Can you hear me? We good? Okay. All right, so I'm Mary Knapp. I'm a research scientist at Haystack Observatory. So I do research on all sorts of things related to radio for my job. And I'm going to tell you about one of the things that I'm working on, which is a concept study. So a very early look at an idea to see if it's reasonable, feasible, possible, and might be able to be built sometime in the future. So that is the Great Observatory for Long Wavelengths. And I'm going to tell you what I mean by that and what it's for. So let me start with our electromagnetic spectrum. So you probably have seen a picture like this. If not, I'll go through it. So what we've got is we have wavelength, so the length of a period of a wave of electromagnetic radiation along the bottom here. And then this brown curve is atmospheric opacity. So if it's at 100%, the wavelength doesn't go through the atmosphere, and if it's at 0, it goes through just fine. So up here at short wavelengths, gamma rays, X-rays, ultraviolet, the atmosphere protects us from those really energetic forms of electromagnetic radiation, which is great for us squishy humans here on the ground, not so great for astronomy. So we actually can't see through the atmosphere to look at the stars in these short, high-energy wavelengths. So we need to build telescopes to do that, and we have done that. Visible light is how I see all of you and you see me, so that goes all the way through the atmosphere, very convenient for us. Infrared, like longer wavelengths than visible light, sometimes passes through the atmosphere. You can see the transmission is a little choppy here. There's a big chunk of infrared that is blocked. And then there's a big radio window. So radio wavelengths like that you can hear in your car or that you can use to control things remotely. Key fobs for your car, they operate with radio, and radio telescopes also are in this band. So we can observe the radio sky from the ground to a point. Right here, we kind of fall off a cliff, right at the low frequency end of the radio spectrum. So I'm going to point over here. And it doesn't show up on the monitor. That's okay. So on the side here, there's a cliff that goes up, and then suddenly transmission goes to nothing. We can't see through the atmosphere at very long radio wavelengths, which is kind of a shame. That's a part of the spectrum we haven't had a chance to explore. So I'm going to talk a little bit about what we might see in that part of the spectrum and why we should maybe try to build a telescope to do that. All right. So if you have ever gone outside on a really clear night in a really dark place, you might have seen something like this. You might have seen our own galaxy overhead. It's kind of a band of stars that's thicker than the rest of the sky. That's our Milky Way galaxy. So for a long time, for most of human history, this is all that we could see of the universe if you had a nice dark sight to see it. But then we built space telescopes. And suddenly we could see the galaxy in infrared, and you can see some views of it here. So when we looked in the infrared, suddenly we could see through the kind of cloudy dust that is towards the center of our own galaxy, and we could see right through to the center, which was a revelation for astronomy. We built radio telescopes, even longer wavelengths, and we could see different views of the same galaxy. You can see that in general it looks roughly the same, but different features are emphasized or de-emphasized depending on the wavelength, right? We built bigger radio telescopes, interferometers, which I'll talk about briefly, and yet again, we have a different view of the galaxy. We also went to the other end of the electromagnetic spectrum, the high energy end. This is X-rays, and then gamma rays. So here is our beautiful galaxy in a multi-wavelength view. And at each different wavelength or frequency, you see different features. You learn different things about how the universe works. There's still a piece missing, though. That low frequency part that I showed you on the opacity diagram, it's still missing. We don't have a telescope for that part of the spectrum. What do we know about the sky in this part of the spectrum? Do we know anything? Is it a complete blank? Well, I'm about to show you the best image we have of the low frequency sky. Are you ready? Okay. Ta-da! Maybe a bit of a disappointment, huh? Compared to those other beautiful images that I just showed you. This was a view of the sky at low frequencies. You can see the frequencies. It's 3.93 megahertz and 6.55 megahertz if you look at those circles. This data was taken 50 years ago with an instrument called Radio Astronomy Explorer 2, or RAE-2. It was in orbit around the moon. It used the moon as a shield so that it could observe this part of the spectrum but without interference from Earth. So it made these maps. They're pretty low resolution, but they were very impressive, for the time and the technology. These are very simple antennas that were used, and they put a lot of work into making even a map that looks like this. Wouldn't it be nice to do better, right? So we have some extrapolated guesses at what the sky should look like at these low frequencies. So here is a simulation. This is not data, although it is data informed, but this is a simulation of what the sky looks like at 10 megahertz. Okay, it kind of looks like those other pictures that I showed you of the galaxy, right? It's bright in the middle, dimmer towards the edges where the galaxy is not. So let's keep going down in frequency in our simulated guess at what the sky looks like. Okay, we go down to 3 megahertz. It looks a little different, doesn't it? That middle part isn't as bright as it was. And if we keep going down to 1 megahertz, suddenly it's completely different. That doesn't look like the pictures of the galaxy that we were looking at in all those other wavelengths, does it? And that's because there's a phenomena that happens around 2 megahertz where plasma, so ionized gas in the galaxy, goes from emitting radiation towards us to absorbing it and blocking it. And this is a really interesting transition if you study plasma in the galaxy. It's predicted. There's some evidence that, in fact, it does happen. But we have these simulations, but no data to check them against. It's really frustrating for both the theorists and the observers to not be able to check the predictions. So we really like to do better than this and actually check that these maps accurately predict what the sky looks like. That would be nice. The reason that we can't see through to the galaxy at these wavelengths is because of plasma. Again, plasma is ionized gas, so the electrons are free to move around, kind of like in a metal, but it's a gas. And so wavelengths that are at much higher frequency than the sort of natural vibration frequency of the plasma, they just shoot right through. So that's why we've got the big radio window that we can see all the way out to space. But when you start to get wavelengths that are similar to how fast the plasma can move, how fast those electrons can move around and rearrange themselves, suddenly the plasma starts to interfere with the transmission of those waves. And that's what happens in the Earth's upper atmosphere, ionosphere. That happens around 1 to 10 megahertz, depending on if it's day or night, if the sun is active or quiet. So we get to a point where, definitely below a megahertz, incoming waves, they just bounce right off, and we can't see out anymore. So going back to this diagram, you see the space telescopes that are on here for the parts of the spectrum at high energy and infrared where we can't see out. So we discovered this problem, we built space telescopes, and now we can see that part of the universe, right? So we have SWIFT for gamma ray bursts, we have Chandra for X-ray, we have Hubble for UV, we have JWST for infrared. Where's my low frequency telescope? We don't have one. RAE-2 was 50 years ago. What have we done since then? not a whole lot. Certainly there has been work and individual spacecraft, but no great observatory like JWST or Hubble for this part of the spectrum. So I found out about this when I was like, I think it was my junior year in college when I was an intern at JPL. I learned about this missing part of the spectrum, and it's bugged me ever since. I can't stand it. I want to know what the sky looks like at these wavelengths. So I'm going to do something about it. That's what GOLO is. GOLO is the Great Observatory for Long Wavelengths, the part of the spectrum we can't access. And it's a concept, it's an early stage idea that we're developing. I'm going to tell you about it and what we think that we'll be able to see with it. So actually, before I get into that, I'm going to let my friend Melody Cow tell you about this project and what we hope to see. Where's my audio?
The entire electromagnetic spectrum. Gamma rays and X-rays through visible light and infrared and even to centimeter radio waves. But we've never seen the sky at the longest radio waves, longer than about 10 to 15 meters or 15 to 20 megahertz in frequency. At these long wavelengths, Earth's ionosphere doesn't allow radio waves to pass through. So the question is, why haven't we built a space telescope to explore this part of the spectrum? It's because a telescope must be many wavelengths across to provide resolution. So a telescope that observes waves tens of meters to kilometers long must be hundreds of meters to many kilometers across. GOLO is an array of spacecraft spanning thousands of kilometers. With GOLO, we'll finally be able to see the low-frequency sky in fine detail. And what will we see? Exoplanets in the solar neighborhood, blinking on and off with radio aurora from their magnetic fields, interacting with stellar winds like fireflies in the dark. These radio aurora carry important information about their planets, whether or not the planet has a magnetic field, how strong it is, how fast the planet is rotating, and even hints about what's inside each planet. Studying exoplanet radio aurora and the magnetic fields that they trace is an important piece of the habitability puzzle, and it's a key science goal for GOLO.
So exoplanets, how many of you are familiar with the idea of exoplanets? Very good. When I was born, and I'm not going to tell you when that was, there were no exoplanets known. We had not yet discovered any planets outside of the solar system. I don't think that's true for most of you. I think probably your entire lives we have had definitive proof that there were planets around other stars, which is pretty cool, right? There's a lot that we know about exoplanets. We can learn about their mass and their size, their radius. We can learn about what's in their atmosphere with JWST. What gases make up their atmospheres. We know how far away they are from their star and what their kind of star they're orbiting and things like that. We don't have a lot of information, though, about their magnetic fields. Earth has a magnetic field, and it's a very nice magnetic field. It lets us figure out where north is, and it also provides some shielding from cosmic radiation, which is good, again, for us squishy humans. We don't know about exoplanets. We don't know anything about whether these planets that we're discovering have magnetic fields, how strong they are, how they're configured, do they vary with age, and what does that say about the likelihood of things evolving, living things evolving on their surfaces. So I'm an exoplanet scientist by training. That's like what I am interested in, and that's what I do. And so, again, this bugged me. I want to know about magnetic fields. And it just so happens that we can learn about them in this low-frequency part of the spectrum. How do we know that? How does that work? So back in the 50s, before we had space exploration, there was a team of scientists who pointed an early radio telescope at Jupiter. And they saw these blips. Do you see the blips on the strip chart? You can see kind of like peaks on this very old strip chart. Those are blips from Jupiter, from the position of Jupiter. They happened with a regular periodicity, and they were quite bright in radio wavelengths. And the scientists who made this observation wanted to figure out, what's causing these blips. That's sort of an odd thing to have happen in space. What's making these blips happen? And what they speculated was that they were seeing what's called cyclotron emission, which is electromagnetic emission caused by electrons spinning around magnetic field lines. And they're accelerating as they go around the magnetic field lines, and they emit radiation as a consequence. And I don't have a ton of equations in this talk. I just have this one here. The important thing is that the frequency that they emit as they're spinning around their magnetic field lines is directly proportional to the magnetic field strength, B, right? That's what's in this equation here. F, the frequency, is directly proportional to B, the magnetic field strength. So under the assumption that they were seeing cyclotron emission from Jupiter, don't do that, there we go. They calculated for the frequency that they were looking at, what is the magnetic field strength of Jupiter? And they got something that actually turned out to be quite close to the answer we got when we finally sent spacecraft to measure directly, to put a magnetometer around Jupiter and check what the magnetic field strength was. So back in 1955, we found out the magnetic field strength of Jupiter through these blips that we detected in the radio, and it was a pretty accurate answer. So that's really promising for exoplanets, isn't it? Because this is something we can do remotely. We can listen for the radio emission, look at its frequency, and figure out the magnetic field strength. So that's really promising. And so the Voyager spacecraft, years later, went and did this for all of the gas giants in the solar system, as well as the Earth. So this plot is the radio spectrum. So the frequency is along the bottom, and the intensity, the flux density, is on the y-axis. And it shows you the radio spectra of all of our solar system planets that have strong magnetic fields. So Earth, Jupiter, Saturn, Uranus, Neptune. Nope. But we had to send a spacecraft. Why did we have to send a spacecraft? We had to send a spacecraft because of the Earth's ionosphere. Jupiter happens to have the strongest magnetic field in the solar system, so we were able to observe it from the ground. The radio frequencies it emits are at a high enough frequency that can get through the Earth's ionosphere. Not so with every other planet in the solar system, so we needed the spacecraft to study them. I want to play something fun for you. So this is data from Cassini, which was a spacecraft in orbit around Saturn, and they've taken the radio data that Cassini collected and turned it into sound. So please enjoy Saturn's radio aurora. What does this sound like to you? Screams? Haunted house? So now you know that Saturn and Jupiter and Uranus and Neptune and the Earth, they're screaming away in radio all the time. And we just need the right instruments to be able to pick it up and learn from them. It's a little creepy when you kind of think about it for a second. I think it's super cool. I love the idea of planets just kind of screaming away in the dark, and I'd like to build something to be able to listen to them. So, how do we do this? All right, so one of the most important things that you need to understand if you're building a telescope to look at a particular thing is how sensitive does your telescope have to be? How hard is this measurement that you want to make? So we know lots about the solar system planets and their radio emission, and that is represented by these colorful curves up at the top of this plot. So frequency is again on the horizontal axis, and then we've got flux density or brightness on the vertical axis. And so we can see that the solar system planets are quite bright. They're up at the top here. And we don't need a huge amount of sensitivity to detect them, right? We did it from Earth with a pretty simple telescope. Voyager 2 is not a particularly large antenna. These dotted and dashed curves represent how many antennas you need to make a detection, okay? So solar system planets, easy, like a couple, 10, sure, whatever. But here's where exoplanets are, based on extrapolation from how bright solar system planets are and then putting them at a distance, right? Maybe giving them a little boost if they're close to their star. So this purple box is where exoplanet radio emission lives. Look how far away that is from the solar system planets. That means it's hard. That means you need a lot of sensitivity. You need a lot of antennas. You need up to something like 100,000 antennas to be sensitive enough to have a high likelihood of picking up exoplanets. That's a lot of antennas, right? That sounds kind of scary. It certainly did to me when I first thought about this problem. So how are we gonna do it? If we wanna find these exoplanets, we wanna listen to their weird, screechy songs, how are we gonna do it? So let's talk about that. Let's talk about the study that we're doing and how we think we can put together a telescope that's capable of listening to exoplanets. So first, you gotta pick the right antenna. So I'm not gonna go into a ton of detail on this antenna. I'm just gonna describe it briefly. If you are curious about it, you can ask me at the end. There's this thing called a vector sensor antenna. And it's basically 6 antennas in a trench coat, okay? It's 3 dipole antennas, it's 3 loop antennas, and they share a common phase center. You can see them in this picture here. You can see the spiky ones, those are the dipoles, and the round ones are the loops. So this is a vector sensor that has been built and used. In fact, it's built by Lincoln folks. And it's a really, really good antenna. This particular configuration is maybe not so great for a spacecraft because it's all big and spiky and rigid. So some very clever folks at Lincoln Laboratory designed a version that you can actually stuff into a box that's about this big. And then when you get to space, you can open up the box and this big antenna spools out and it looks like this. So I know these look very different. You're gonna have to take my word for the moment that they are electromagnetically the same. They behave the same way in terms of receiving signals. They have a major advantage over, and if you're interested, there's papers about it here. They have a major advantage over sort of just a set of dipoles, like just a set of those sticks. They collect more information, like more quickly. And what that means is that you can collect the same amount of information with fewer antennas, which is really good for a space mission. It's very efficient, and it means that you can get to your 100,000 antennas, and that's enough for the sensitivity that you need. Again, if you're really interested, there's like papers on this. I can talk about it more in the Q&A, but I'll just leave it there for now. So we think a vector sensor is the right antenna for this task. So that's the one we've picked. The most information, most bang for your buck. Where are we gonna put it? Where are we gonna put this telescope? So there happens to be these special places in space, in any two-body system. So let's say the sun and the Earth, right? Big, massive sun, little Earth. There are places in that system where their gravitational potential balances, where you kind of have equal pull from the sun and the Earth, and you can kind of find a balance point. There happen to be 2 of those, these are called Lagrange points, ahead of and behind the Earth in its orbit. So you can see them marked as L4 and L5 in this figure. And those are really nice places because if you put something there, it's not going to float away. It will just stay there, which is really nice if you want to put a big telescope with many, many pieces in one of these locations. So we think that the Lagrange points, L4 and L5 specifically, are the right place to put this telescope. And I'm going to let Arthur tell you a little bit more about what that looks like.
The constellation is deployed into 3 nearly orthogonal planes. The satellites execute a regimented pinwheeling motion that allows for straightforward traffic management along the lines of intersection. And they can be set out so the satellites can stably and predictably take turns passing through those lines. As we zoom out, we see the constellation centered around L4 in the context of Earth's orbit around the sun. Note the geometry and how the orientation of the planes follows Earth's orbit. This configuration exposes a full cross-section, ideal for beamforming to all directions in the sky at all times. And once at the Lagrange point, Deployment costs are modest, no more than 1 meter per second of delta V per satellite. And fuel requirements for constellation stability are also modest, estimated to be less than about 2 meters per second per year per satellite.
All right, so we have an antenna. We have a place to put the antenna, and we know approximately how many antennas we need. So what do the spacecraft look like? How do we do this? Do we want every single one to be the same? That would be nice, at least they'd be redundant. They would only have to build one kind. So that obviously is ideal, but okay, can we do that? What we need is a lot of these, right? We need many antennas to get to that 100,000. So that's a really important requirement as we work through this design, right? We also want to minimize how many launches, how many rocket liftoffs it's going to take to get all these into space, because that's expensive, right? So we need a lot, but we need them to fit in a small number of rockets. That kind of means they have to be small, right? We also need them to be able to communicate. We need to be able to get all this data that we're going to collect back to the Earth. The most efficient way to do that, especially for large data rates, is with laser comm. Any of you touch on laser comm in your programs? Not really, okay. It's basically just using lasers to send information, and you can send a lot of information really, really fast with laser comm. It's a great way to send data through space. So we considered different shapes that these spacecraft could have. We looked at CubeSats, which are kind of like loaf of bread shaped things. We looked at DiskSats, which are big, wide, but very thin disks. And the conclusion we came to is that we kind of actually had to have two different types. We had to have little guys that were basically just an antenna with a spacecraft kind of wrapped around it. So that makes up most of the constellation. We call those listeners, okay? Their job is to collect radio data with these antennas, and that's about it. We also had to have larger spacecraft, a smaller number of them, that kind of shepherd these listeners, collect data from them, and send that data to Earth. And they're big enough that they can have a laser comm system. Laser comm systems are really efficient, but they are kind of bulky. So you need a bigger spacecraft. The listeners are 3U CubeSats, so that's like loaf of bread sized. The communication and computation nodes, the bigger ones, they're like mini fridge sized. So, that's bigger, but it's not, as big as some satellites are. So this is our compromise. So here's how this works. The listener nodes are these little guys. The communication and computation nodes, or CCNs, are these bigger guys. And the listeners collect science data. So here's an exoplanet sending out a auroral radio mission. They transfer the data that they've collected, listened to the CCNs. The CCNs do some number crunching on that, and then they use their laser comm system to send that data to Earth. So that's the architecture that we have come up with for this constellation so far. I'm happy to answer questions about stop going forward. About other options we considered, or other ways you might do this. So the last question is, how do we launch this thing? And so we looked at some of the architectures for heavy lift, like large volume rockets like Starship. And Starship has this idea of refueling in orbit, which is kind of nice because you can lift a lot of mass off the ground and then fuel it up in orbit and then send it on to wherever it's going. Obviously Mars is the concept for Starship, but we want to go somewhere else to these Lagrange points. And we calculated that we can fit 21,000 spacecraft in a single Starship launch. That's a lot. That's a lot of spacecraft in one rocket launch. And that means that we can do this for 5 to 6 launches to get everything where we need to go, which sounds like a lot, admittedly. But again, this is a big long-term project. And so this is what we come up with. I want to talk a little bit about the benefits of this being a constellation. This is a constellation of spacecraft that are somewhat functioning independently. Why is that a good thing? Well, it's a good thing because you can grow it over time. One launch goes, next year another launch goes, and then 2 years later another launch goes. So you build up over time, which can help with budget stuff. You can also replace spacecraft that fail. Everything you build has a finite life, right? Parts fail, particularly in space, which is a very harsh environment. So when parts fail, you can replace them. That is not something you can do with JWST. And finally, you can move them around. That's really cool. For radio science, for interferometry, where you're building this big virtual telescope, being able to reconfigure it, move parts around, maybe move them farther out, maybe bring them closer together, gives you a lot of flexibility about the science that you can do. I also want to talk about what it means that you can build this up over time. So we looked at the sensitivity plot with the solar system planets. You don't need a lot of sensitivity. You can do a lot with just a couple of spacecraft. So you can start with like 10. And you can do tons of really cool science within the solar system, looking at the sun, looking at the ice giants, Uranus and Neptune, which are very poorly explored. Then you build up to 100, and suddenly you can start making amazing maps of the sky with 100 antennas. And you can start doing some cosmology. You can start looking back in time in the universe to understand what was happening as the universe was still forming. Then you get to 1,000, and suddenly your maps are amazing. And you also can really knock out the cosmology problem. You can get some really important answers to questions that we've had for a long time about what the very early universe was like. If you're curious about that, ask me at the end. And then finally, you build up to your full size, 100,000 spacecraft, and then you can finally do exoplanets. So I want to finish just by sharing some photos of the team that's working on this. We have a really great team that I'm really privileged to lead. We have members from Lincoln Laboratory, from Cornell, from Lowell Observatory, and Leaf Labs, which is a local consulting firm. So we have a great team. We are working on this study. There's lots that we're going to do in our next steps. I'm not going to go through all of this, but we're studying in more detail, like logistically, how do you make this happen? Like, how do you control a constellation this big? What needs to be autonomous? What needs to be controlled from the ground? What does that autonomy look like? Lots of stuff like that. So that's what we're getting into. That is, work that we are doing at the moment, still to come. So stay tuned. Maybe next year or in a couple years, you can hear a lot more about what we have come up with in that part of the study. So I'm going to stop there, and we have lots of time for questions.
So Sigrid, you want to start with a couple from online, and then we'll pick some from the room here.
All right, perfect. I'm going to select Ethan Lin to be our first online question.
Hello, thank you so much for your presentation. It was really cool hearing about your idea of like having an army of like satellites in space. I was wondering about do you guys have any concern over like the space debris that might kind of like damage all these satellites, and the fact that if any of these satellites are broken and can't be repaired, it might be generating more space debris? Would that be like a problem for if you do execute the plan?
Yeah, that is a great question, Ethan. So I actually get this question almost every time I give this talk because there's a lot of concern, and rightfully so, about space debris. In low Earth orbit, right kind of above our heads, it's becoming an almost critical problem. We're putting our constellation far away. So the spacecraft that we put out at L4 or L5, they're never coming back. They'll never come back to the Earth. They won't contribute to the low Earth orbit space debris problem, and they kind of will stay where they're put. So, it does open up possibilities for a future where we could go get them. We could go get them because they're just going to be where we left them and recycle them. So that's one possibility. It's a little bit beyond the scope of the work that we're doing. But the fact that they are in a place in space where we know where they are and they're not going to go wandering off is kind of the best we can do at the moment for mitigating any issue with space debris. At the very least, they're not going to come back and hit anything in Earth orbit ever for thousands and thousands of years. Great question.
All right, next I'll select Prahalat.
Hi, thank you so much for your talk. I had a question about what do you anticipate the impact of the sun and its radiation doing on the constellation of satellites? Because I'm in the basics of ASICS course right now, so I know a little bit about how radiation can sometimes do bad things to computers that you don't want, and how would you combat that issue?
Another great question. So it is definitely true that space is a harsh environment, and radiation, particularly from the sun, solar energetic particles, can kind of punch holes in your electronics and make them into Swiss cheese, and then they don't work so well. So there are a variety of ways that you can mitigate that problem. You can build like physically larger processors. Obviously, for ground-based applications, everything is pushing to smaller and smaller and smaller, lower power. For space, sometimes we actually go the opposite way. We build physically larger devices because then when you get particles punching holes in them, they're a little less likely to hit something critical. So they last a little bit longer. You can also shield, you can put aluminum around things, which blocks some of the radiation. And you can also do software redundancy type things. You can either physically have redundancy, like multiple processors that are the same and they check each other, and you can also do similar things in software. So there are sort of well-established ways to deal with radiation effects for space hardware. In our case, we have the extra advantage that some of them are gonna fail. Some of them are gonna get that particularly bad radiation hit and it'll kill them. Okay, we have, 100,000 more and the ability to send more to replace the ones that fail. So there will be some failure rate, and that is actually okay, which is really unusual for spacecraft.
Okay, so we're gonna do 2 in person.
Hello, my name is Sophia. I'm a research student for the Autonomous Underwater Vehicles course. I was wondering, what are the similarities behind of the science behind low glow and the science behind the network of telescopes that captured the image of the black hole?
That's a fantastic question because the underlying concept is interferometry, and it's the same. So the Event Horizon Telescope, which is, with which Haystack has significant involvement, by the way, it's an interferometer. It's telescopes scattered across the globe, and they collect data, and then the data is brought together at Haystack and combined in order to make something sensible, which eventually becomes the image of a black hole. And interferometry is the technique that makes this work. It allows us to basically, you can think about having a telescope that's the size of the Earth, right? And we only actually have the ability to receive signals at a few specific places where those telescopes are located. So it's like a mirror that's mostly black except for a few shiny parts. And with a lot of math, you can put together the shiny parts and make an image out of it anyway. GOLO uses exactly the same concept. It's an interferometer. It has nodes that collect data, and then they send them to a central-ish location, and we do the math, and we make an image out of it. So the only difference is, the frequencies. The black hole telescope works at much higher frequencies than GOLO does, which actually makes GOLO's math challenges easier because the wavelengths are longer, the precision can be a little fuzzier. But you correctly identified that the same math is happening in both cases.
All right. Thank you so much for coming here today. I wanted to ask, because at the very start of your sort of presentation, you talked about how at the 2 megahertz point, there tends to be sort of interference from plasma. And I'm not sure, would the go low sort of network, would that operate in the, around this range? Would it be affected by the plasma interference? But if not, then how would you generally combat this issue? How would you, try to sort of go past or go beyond that sort of interference?
Another great question. So what's happening at the sort of 2 megahertz turnover is you're going from an emission regime where the plasma is emitting radiation sort of at you, and you can pick it up with telescopes, to absorption. So that what that means is the sky gets foggy, is the way to think about it. So the center of the galaxy is very bright. There's a lot of energy there, and so there's a lot of plasma. It's dense and it's emitting, right? But the intervening plasma at around 2 megahertz suddenly stops being so clear. You can't see through it as well. And so you get this turnover point, and suddenly it's starting to block partly that bright galactic center. And it isn't quite so dense up at the poles, the galactic poles, and so you can see through farther. So you can think of it as like a fog that gets foggier as you go down in frequency. And so what that means for GOLO is, we'll map out that turnover, right? And what it looks like, which tells us something about the density of plasma everywhere we look, right? Like how foggy is it? It tells us how dense the plasma is. It does mean that, at low frequencies, our frequency range is 15 megahertz to about 400 kilohertz. So at the low end of that, we're only going to kind of be able to see our local neighborhood because the fog will be dense enough that we won't really be able to see out to other galaxies, except maybe up kind of through the poles.
Thank you so much.
Over to Sigrid for a couple more online.
Yep, I'm going to select Alex. Alex, if you could ask your question.
Thank you for your presentation today. I was wondering how you split up the computation between like the satellites that are doing aggregation in space and like ground-based computation devices.
Another fantastic question. So the current architecture has the CCNs, the large spacecraft that do some number crunching in space. It has them do what's called beamforming, where they take all the data from their listener nodes, their little cluster of listener nodes, and they basically turn it into one data stream. They make kind of a virtual telescope like that's a part of the array, and they take that and make it into one data stream. But there are many CCNs scattered throughout the constellation, and so they aggregate the data from their little cluster, and then they take that aggregated data and they send it to Earth where we continue doing more correlation. That's where the correlation happens and we make images and things like that. So we've kind of split it in half. You know, the aggregation happens in space, but then we bring as raw data as possible down to the ground so we can do lots of different things with it with all the computation we have available on Earth.
Great, we're going to have Nishka ask next.
Yeah, I was just wondering if all of these like 100,000 satellites could like detect maybe a message from aliens, and if that's like a goal for Golo.
Yeah, fantastic question. So it's possible. When we were in the early days of radio communication for the Earth, we did a lot of communication at fairly low frequencies because they travel long distances over the ground. Some of that signal is blocked by the ionosphere. You know, the same reason that like we can't see out, it also keeps our signals in, if that makes sense. So, you know, but different planets will have different ionospheric plasma frequencies, and so, you know, more or less of their communication signals might escape. So it's certainly possible that we could pick up, you know, a non-natural signal that has structure to it that is potentially a technosignature. It's not it's not the top goal of GOLO, but whenever you look at a new part of the spectrum, you see things you don't expect. And maybe that is something that we would see that we didn't expect. There's no reason to think that the technology progression that we went through is, you know, couldn't be repeated for some other civilization.
Hi, thank you so much for your presentation today. I had one question. When you actually send the satellites or your constellation of satellites to your Lagrange points, how do you ensure that your orientation toward like the orientation of the constellation towards Earth, as well as the orientation of your listeners out into space, how do you make sure that those stay in the orientation you want them to be? And since there are so many different sets of listeners and aggregators, how do you ensure that they don't perturb one another's gravitational fields, and so they don't crash into each other, essentially?
Yep, that's another question I get a lot because it's a good one. So in terms of figuring out where they are and making sure they're oriented properly, mostly they just need to be oriented so their solar panels can see the sun because that's their power source. That they can do autonomously. So each one is responsible for making sure its own solar panels are pointed at the sun. And if something goes wrong, it basically has to call up its local CCN and say, help, I have a problem, and then we'll deal with it. In terms of their positions, the gravitational potential in that part of space, the L4 and L5 points, it's pretty uniform. So once you sort of put them in an orbit, there's not a lot of perturbation. So there's not much to sort of push them out of where they're supposed to be. And that was the idea with the three-plane thing that Arthur talked about. Once you get them going, they kind of just go. And something unusual has to happen, like a thruster gets stuck on for them to be perturbed from those orbits. We do have to track their positions, and that's actually the subject of our current work on this concept study, is how do we do that efficiently? The best we've come up with so far is something GPS-like. We basically set up the CCNs as a GPS constellation for GOLO, and then each individual listener can calculate its own position from the GPS signals that it receives. This actually turns out to be an easier problem in like free space than it is for Earth, which is great. So yeah, it's kind of like a GPS style localization, and they'll like phone in their positions to their CCNs, and if an adjustment needs to be made, they'll be commanded to do that.
Thank you so much for your talk. And I was wondering, you put up a graph like saying which like sections of the frequency that we've been able to record and see. Do you think that there's anything valuable like beyond even this low level, like maybe even like further beyond, or even higher, like beyond gamma ray? And what do you think might be there to find? And do you think it's going to be like a forever advancement? You got to keep going to the next and next furthest one, or from wherever we are now?
So at the low frequency end, you reach a point where you're in this plasma fog, and you know, the universe is made of plasma. Everything is plasma of different densities and temperatures. You go low enough, and you kind of only can see the plasma around you. Everything else is kind of blurred out by the effects of plasma on your measurement device. There's lots of interesting things to learn about plasma and how it works, especially in like space-like environments with very low density and low temperatures. But those become local measurements. You lose the ability to see out. And so, you know, there's some interest in doing that to understand our plasma environment, but you don't kind of get the astronomy. It's plasma physics at that point. On the high end, the higher you go in energy, like up to gamma rays, the fewer things can make things that energetic. So you kind of end up with like a diminishing returns kind of thing. Like the number of photons that are, you know, super extra gamma ray bright is not going to be very many. They will tell you about the most energetic processes in the universe, and there's definitely lots of work still being done on gamma rays. Like gamma ray bursts are a brand new thing in astronomy. Like we didn't really understand that those existed until pretty recently, and we're still trying to work out like where do they come from, how do they work. So yeah, there is still things to be learned at that very high energy side, but there is a point at which like there just aren't that many things that are that energetic.
All right, over to Sigrid again for a couple online.
For online, we'll have Han go first and then Jimmy go second.
Hi. I think my first impression from your proposed project is the scale of the project, right? Your goal is to have 100,000 of these satellites out there. And well, you know, we start with 10. So would budget or getting funding be a limiting factor to get that first 10? And is there ongoing research of trying to reduce that cost so this project becomes more and more feasible?
So this is something I didn't touch on in this talk because, you know, I have time limits. So we are in the midst of a real kind of sea change in how satellites are built, right? Have you all heard of Starlink? Yeah. Okay. Starlink is tens of thousands of satellites, and it's growing almost daily. So those are mass manufactured satellites, and they are built with an acceptable failure rate, right? They deorbit pretty quickly, so they have to be replaced. This is a paradigm shift for building spacecraft. And this fact of mega constellations, whatever you may think of Starlink and the other companies making them, we're doing it, right? We're building thousands and thousands of satellites in a mass production sense. So that will drive our costs down, right? Not having to build each satellite as a special bespoke snowflake, building them in a factory and just cranking them out and accepting that some of them won't work, that brings costs down significantly. And that's one of the reasons that we're doing this concept study now, because we're in this new world where you can do that, right? That said, like, this is not meant to be like a shoestring cheap mission, right? JWST was well in excess of $10 billion, right? That's the kind of scale that great observatories are on, right? They're multi-billion-dollar missions because we as a scientific community hopefully decide that it's worth it. It's worth that investment to learn something new about the universe. So, you know, that's the kind of scale we're talking about, and that's why this is a concept study now, so that maybe in 20 years or 30 years, we can have enough momentum and enough support from the government of the US and hopefully of other countries as well to do this, to make that investment.
All right, Jimmy, you can ask your question.
Hi, I'm Jimmy. I was just wondering if a previous person talked about extraterrestrial life and stuff like that. If you've ever collaborated with the Harvard Galileo project, in a broader sense, like why collaboration with other organizations like these are important, and like how do you balance the profit incentive of like private organizations and with the need for getting research grants with just like the pursuit of scientific knowledge and advancement in the field as a whole in general? Like, is there any like collaboration, and like how is that emphasized, or how is that like more nuanced due to like financial measures?
Yeah, that is an interesting question right now. So without getting into the whole federal funding situation, so yeah, collaboration is very important. And I think particularly for a project like this, collaborating within the scientific community in the US, but also internationally, is really, really important. Ideally, this should be something for everyone on Earth, right? The knowledge that we would gain from a telescope like this should be for everybody. And so it makes sense for that to be a collaborative effort, both within this country and around the world. So, you know, we're not like quite there yet, right? Because we're just trying to make sure that this can work. But that is actually kind of the next step, you know, building those collaborations, building consensus that this is worth doing, and, you know, getting this into the plans for the US government and hopefully other countries as well to fund. Basic research is not profitable like in the moment, right? It needs to be supported by usually the government because you're kind of exploring and you don't know what you're gonna find when you're exploring. And that's okay because usually you find something interesting. Even if it isn't the thing you set out to find, usually you find something interesting. You may be familiar with you know, research on the saliva of a lizard has led to the development of Ozempic, the drug, right? So when the people doing the lizard research were doing that, they weren't doing it to do drug discovery necessarily, but it happened that they found something interesting, they found an interesting compound, and they could turn it into a drug that is enormously profitable. So you have to have a balance, I think, between government funding of basic research, which has to be exploratory, it has to be open-ended, or you're not gonna make progress, and then also, you know, private sector investment in application of what comes out of basic research, right? So, you know, in our case, the science that we wanna do, probably the instrument development as well, that kind of falls under that basic research umbrella that really needs government support. Building the spacecraft, however, is potentially a profitable thing for private industry to do. You know, building one or two, maybe not profitable. Building 100,000, now you're talking, right? Now you can leverage private industry and the profit motive of private industry to build something for science. You know, paying the scientists to analyze the data, that's basic research. No company is gonna do that because like, what's in it for them, right? Building the stuff, different story.
Hi, thank you for your presentation. So at the beginning of your presentation, you mentioned that that low-frequency radio waves can be used to identify what's in exoplanets. I was just wondering what exactly you can glean from that and how you can glean that information.
Yeah, great question. So, okay, this planet that we're standing on, we know through various means that we have the crust, the solid rock that we stand on and everything that we know is on, the kind of solid but mushy mantle that's underneath that leads to the movement of continental plates. And then in the center of the Earth, we have a liquid iron core and then a solid iron core at its center, right? And it's in that liquid iron core that our magnetic field is generated. So generally speaking, to have a magnetic field at a planetary scale, or in a star, if you like, you need an electrically conductive fluid that is convecting, that is turning over either through heat or composition or both. So you know that if you see a planet with a magnetic field, somewhere in its interior you have those conditions, because otherwise the magnetic field wouldn't exist. So, for Earth and in the past for the Moon and Mars and currently for Mercury, it's an iron liquid that's doing the convecting, right? For the gas giants, it's a different thing. It's either metallic hydrogen or a very high pressure form of water that is basically conductive. So if you look at an exoplanet and you see it has a magnetic field, you know that somewhere in its interior, that condition is met. And then you can use other information, like its size, its composition, its temperature, to start to narrow down, okay, what is that convecting conductive fluid? And from the geometry of the magnetic field, you might even be able to figure out like how far up in the cross-section of the planet does that fluid layer exist.
Thank you.
Hello, I was wondering if you guys had any plans of, what your plans of scaling this project up, and if this project could lead to any bigger discoveries in the space community?
So we're kind of have our heads down, and we're doing this study right now to show the feasibility of this concept and how we might execute it, and also what technologies need to be further developed before we can actually do this. The longer term goal is to do a demonstration. So launch 10, 20 spacecraft and try out some of the techniques that we're developing in this study for autonomy, for in-space data assimilation, and do some early sort of reconnaissance of the radio universe at these frequencies. So that's like the next sort of near-term step, and there's lots of possible ways in which that could be funded, government funding, potentially foundations. We're working on that. I don't have that lined up quite yet, but we are working on it. In terms of sort of like what big discoveries do we think we'll make? So exoplanets are my thing. That's what I talk the most about. Learning about the full picture of a planet from its atmosphere to its interior is big. I mean, just the atmosphere is a big deal with JWST right now. More broadly within the physics community, the cosmology is really exciting, because what you can do is you can look at very highly redshifted hydrogen that basically shows you the early universe. And at these frequencies, the hydrogen emission line is at 1420 megahertz. So we're talking about 15 megahertz and down. So that is a lot of redshift, right? To go from 1420 megahertz to 15. It's a huge redshift, which means you're looking way, way back in time. You're looking at the time before there were stars. So with GOLO, we can explore what's called the cosmic dark ages, the time before stars had formed and lit up the universe again. And so that is a part of the sort of cosmological timeline that is basically impossible to explore from the ground. And so if we want to make progress in testing our theories about how the universe evolved, that's a measurement we need. And that, for the physics and cosmology community, is a big deal.
Right, we're going to wrap things up a little bit here. I will say I love the fact that she went through the science behind the engineering to justify the size of the constellation and everything behind it. It was great engineering behind that. I loved that. So Sigrid, I'm going to turn over to you for a minute.
Yep, I'd like to look up Abigail and Horton from our microelectronics course to do the t-shirt presentations.
Hi, I'm Horton. I'm from the microelectronics course.
Hello.
And my name is Abigail Argueta-Vigil, and I'm also from the microelectronics course.
So I've actually done a bit of research on millimeter wave radar for human detection in the past, so I'm pretty familiar with the electromagnetic spectrum, especially in the radio wave and microwave frequency. And after seeing your talk, I think the coolest part was basically seeing that the same principles I use for my own personal project is also used by professionals like you at MIT Haystack to explore the atmosphere and also space. And ultimately, I think it shows just how interesting electricity, magnetism, and light really is.
I completely agree.
Yeah. And I found it really interesting how someone explored blips from Jupiter just out of curiosity, which led to the identification of magnetic fields remotely. This really stood out to me because this story is an inspiration to us on how we should explore the unknown and most random things as engineers. Just like how we're exploring so many things in BWSI, and just like the example with the lizard you gave us. Now, we would like to thank you with the BWSI t-shirt.
Oh. Thank you very much.
Let's thank Dr. Knapp one more time. Thank you very much. So we don't have any announcements. So are you able to stay for a few minutes and answer questions for in person? So super. Thank you, everyone. Thank you, online students, for your questions and paying attention and being here. So any preferences on dismissal? No. All right. Why don't we